Hello there. In this video we're going to look at continuing the motion in magnetic fields topic and talk about circular motion in magnetic fields for our moving charged particles. So to talk about circular motion, we're going to use this magnetic field here that's in this space going into the page, and we're going to talk about this positively charged particle here with a velocity going up and this negatively charged particle here with a velocity going up as well. We'll focus on the positive charge first. We should be able to recall that we can determine the direction of the force on this charged particle by using the right hand palm rule. So if we place our thumb in the direction of the velocity here and our fingers in the direction of the magnetic field, which should be into the page, we should convince ourselves that the direction of the force on this charged particle should be going to the left. So there's the force on it that's going to the left. So this charged particle, it's got its velocity at right angles to the force that's on it. And what that's going to do is change the direction of the velocity, but the magnitude of the velocity, the speed, is going to stay constant because no component of this force is pushing the velocity and increasing it or decreasing it. So the velocity will change direction and the particle will kind of curve and go to a different point later in time. So here's our particle. If the force wasn't there, it would have just kept going in a straight line, but because this force is there, it's been nudging the particle and turning it to this later point here. And if we use the right hand rule again, we point our thumb in the direction of the velocity and fingers in the direction of the magnetic field, and the force ends up being still pointing at 90 degrees to the velocity, and the direction of the force has actually changed such that it's always at right angles to the velocity. So there's our new force vector there, which from our perspective it looks like the direction of the force has changed, but it kind of hasn't changed because it's still just at right angles to the velocity. And what it's going to do is keep turning the velocity because that force is at right angles to this velocity, so it's going to turn it again. And that will keep happening as the particle makes its way all the way around. It'll end up traveling in a circular path. So more completely, this is the circular path that the particle will take. So this is our positive charge with the force on it due to the right hand palm rule, always at right angles to its velocity. This is going to change the direction of velocity while keeping the magnitude constant and put it around a circular path, and at all times, as you can see, the velocity and the force are at right angles, which is the requirement for a circular path. It causes centripetal acceleration and the circular path we see. Now, how is this different for a negative charge? Well, as you might have guessed, the direction of the force will be in the opposite direction, and again we can confirm that with the right hand palm rule. But the force is still at right angles to the direction of the velocity, and so it's still going to change the velocity direction but keep the magnitude the same, and it will send it in a circular path around this way. So we end up getting it moving in still a circular path, but circling it in the opposite direction to the positively charged particle. So this one's going to go around in a clockwise direction, whereas the positively charged one we saw was going in an anti-clockwise direction. So altogether we can explain why these charged particles move in a circle. To get them to move in a circle, we need the velocity of the charge to be perpendicular to the magnetic field. If this is the case, then by using the right hand palm rule, we can see that the direction of the force is going to be perpendicular to the velocity. If the force is perpendicular to the velocity, that means it's going to change the direction of the velocity, but the magnitude of the velocity is going to be constant, and that will cause the centripetal acceleration of the object and make it go around in a circle. And that's why charged particles move in circular paths when they're moving at right angles to a magnetic field. Something to be aware of is oftentimes our charged particle won't be like entering the field like in the middle of it, if that makes sense. If we look at our previous example, these field lines I was doing here, like the charged particle is already in the middle of the field, so it kind of is able to complete its circular path as if it was, say, in something like a cyclotron or something like that. But in this case here, it's kind of entering the field from a different position. So over here there is no magnetic field, so presumably it was travelling at a constant velocity, and then now it's starting to enter the field. It's going to travel in a circular path, and it's either going to do a circular path this way or that way, depending on whether the charge is positive or negative. So we can check that by confirming, well, if I just draw a path, we should be able to tell. Here is a circular path that it could have gone in. Notice that if it's coming into the field from the outside, it can't really complete its circular path. So if a student, say, in an exam did something like kept the path going and made it go around in a circle, that would be incorrect, because when it leaves the field in this region here, it should just go off in a constant velocity in one direction, because it's now left the field, so it shouldn't be travelling in a circular path anymore. So over here, once it leaves the field, it should just go off in that direction there. While it's in the field, it's travelling in a circular path, and you only see like a segment of that path if it was entering the field externally where the field is not. So a concept you might need to know is, well, just from looking at this path here, what charge is this? Is it a positive charge or a negative charge? Because the direction of the path, whether it's going kind of clockwise or anti-clockwise, depends on what type of charge it is. If you look at this situation here and pay attention, we should be able to convince ourselves that the force on this charge should have been upwards to begin with, to get it starting to go around that path there. And then we can use our right-hand rule to confirm whether it's positive or negative. So the force on the charge, at all points along this path, is going to be pointing towards whatever centre this circular arc is. And if we use our right-hand rule here, and make sure our palm points in the direction of the force, and our thumb is pointing in the direction of the velocity of the particle, and our fingers in the direction of the magnetic field, we end up making a shape with our hand that describes the situation, where our thumb's in the direction of the velocity, our fingers in the direction of the magnetic field, and we notice that we end up pushing in the right direction here, which means that this must be a positive charge, because if it was negative, we end up kind of pushing backwards and having to reverse the direction of the force. So this one here must be a positive charge. If it was a negative charge, I'll just draw the path for a negative charge down here. For a negative charge, the path would more look like this, and the force would again be at right angles to velocity at all times, so the force is doing something more like this, always at right angles to where its velocity would be along that path. And then we'd end up pointing our thumb in the direction, then our fingers in the direction of the magnetic field into the page, and if we just think in terms of our palm, it looks like our palm's pointing the force in the wrong direction, and that's telling us that, this must be a negative charge because the force is in the opposite direction as it will be for the positive charge, so it's going in the backhand direction, if you like. So there we go. So for our next discussion, we're going to introduce another positive charge here, which means that its path is going to curve upwards in this diagram here, just like this positive charge, but its path is going to be slightly different. Path is going to look like this. So the center of this circular path is going to be like somewhere way the hell down, somewhere quite far away. If it were to complete its circular path, it would take quite a long time because that's a big circle compared to this smaller circle, which might fit into where I've got the frame here. So what's changed to get us these two different paths? And there's a number of things that would give us this kind of difference between the two, and there's a nice equation that helps us describe what might be different to result in these two different paths. If I were to describe the difference between these two paths, I would say that this path has a larger radius, because they're both circular paths, because they're charged particles in magnetic fields. But this one's got a bigger circle, so it means that the circle must have a bigger radius. And there's an equation that tells us how the radius relates to some quantities. This equation here, the radius of a charged particle in a magnetic field is given by mv divided by qb. And there's some proportionalities that arise here that can help us describe what's happening here to give us two different paths. If we look at the numerator of the equation, radius is proportional to the mass, which means that this particle here with the larger radius might have a larger mass because they are proportional to each other. If we increase the mass, we can increase the radius of the path. So this might be what's occurring here. Alternatively, this particle could have been traveling faster. Radius is directly proportional to the velocity of the particle. So this particle here with the larger radius could be traveling with a greater velocity. Alternatively, if we look at the denominator of the equation, there's the charge and the magnetic field strength. Radius is inversely proportional to the charge, which means that if we have a larger charge, we'd actually get a smaller radius. Which means that this charge here might be larger. So this might be, I don't know, double positive, like doubly more positive. So if it's got a greater amount of charge, it experiences a greater amount of force. It ends up having a tighter curve to its path and a smaller radius. Or alternatively, we could look at the magnetic field strength. The greater the magnetic field strength, the smaller the radius of the path. Because if we increase the magnetic field strength, we should get a greater amount of force on the particle. So this magnetic field here that we're talking about might have been at a lower size for this particle, resulting in a greater radius, and the magnetic field strength might have been greater for this particle here, resulting in its smaller radius. So we can use the proportionalities pretty handily when talking about the different paths that we're getting in the magnetic field. To show us this video, we're going to derive this relationship, the radius between the mass, the velocity, the charge, and the magnetic field strength. We're going to start off by recognizing that this equation is for the radius of the circular path for magnetic fields and charged particles in those fields. So we need an equation that relates to circular paths and that kind of thing. So we'll start off with centripetal acceleration, which always applies if we have something moving in a circle. If we have a circular path, that means we have centripetal acceleration. The acceleration is the speed squared divided by the radius. Now, if we combine this equation with Newton's second law, that force equals mass times by acceleration, Newton's second law, and we substitute this acceleration into this A here, we get the force is equal to the mass times by the speed squared divided by the radius. Now, this relationship here is true for any circular path. What we need to do to get to here is to recognize that the reason why it's traveling in a circular path is because this force is provided by the magnetic field. So we need an equation that talks about the force due to a magnetic field for a charged particle. The force due to the magnetic field that causes the acceleration, and that force, the force due to a magnetic field, is this equation here, given by QVB. Notice there's no sine theta here because in this case, well, if I did include the sine theta, I should immediately realize that, well, here for a circular path, it's when the velocity is actually at right angles to the magnetic field strength. So the angle here, the theta, ends up being 90, and we end up getting back to just QVB. For the case of circular motion in a magnetic field, this is true. And we get sine theta to be just 1 because the angle is at 90 degrees. So F equals QVB is the force due to the magnetic field, and then we're going to combine this equation. So if we call this number 2 and this number 1, we're going to end up substituting 2 and 1 together and setting them equal to each other because this force is causing this force. Because 1 is equal to 2, we get this relationship here. Multiply both of this equation by r, we'd end up with this r cancelling out with that one, so we get r on the left hand side as well. Gives us rqvb equals mv squared. Divide both sides of this equation by qvb, we end up getting that cancelling out with that, leaving us with r on the left hand side of the equation by itself, just as we need. Thus r equals mv squared over qvb, and then this v cancels out with one of the v's up here. Cancellation occurs, this v with one of the v's up here, so we just get mv up the top and qv down the bottom. Thus that gives us the equation we've been looking for. That brings us to the end of this video talking about charged particles moving in magnetic fields. Thank you very much for watching, and I will see you next time.